beginning though. Okay. So I'm very happy to be speaking. Thanks to the organizers for this opportunity to speak. And I'm going to be telling you a story about the Gordon-Litherland pairing for links in thickened surfaces. And this talk is based on 3 papers, 2 of which have appeared at least on the archive, and there are their call numbers. So here and here, and then 1 is in preparation. So the beginning part will be we'll start with that paper, and that's joint with Homoyoon Karimi and Micah Chrisman, and the other 2 are joint with just Homoyoon Karimi. And a word to my sponsor. Of course, I'm very grateful for grant support through NSERC. All right, so the story is really a story about signatures of knots and we want to do this for knots and links and thickened surfaces. So let me start going way back to the classical definition of signatures, and assume K is a knot with a ciphered surface F. The standard textbook definition for the knot signature is you take a ciphered matrix, so that's just the linking matrix over a basis for the first homology of your surface. You symmetrize that matrix, namely you add it to its transpose, and you note that that symmetrized matrix, its signature is invariant under unimodular congruence. So it's actually independent of the choice of the basis, and that defines an invariant of the knot called the knot signature. So Gordon and Litherland made some really outstanding contributions to the theory of signatures. In 1978, a very influential paper where they showed how you could compute the signatures from a possibly non-orientable spanning surface. So for the rest of the talk, F will be an unoriented surface with boundary the knot, okay? And they defined the signature, they gave really a formula for the signature in terms of the signature of an associated pairing plus a correction term. So let me try and describe the pairing and the correction term. So the pairing is defined, so in the previous case, we could push curves in the negative direction and define a linking pairing that way. But with an unoriented spanning surface, that's not possible. What you can do is you can push in both directions, which is the same thing as taking the transfer map, which is a map from H1 of F to H1 of the oriented double cover. So geometrically, what we do is we think of the spanning surface inside S3, we take a tubular neighborhood of it, called that N, and take the boundary of that tubular neighborhood. That will be typically the oriented double cover when F is non-oriented, and it will just be 2 copies of F when F is oriented. The transfer map essentially is a sort of doubling procedure on elements in the first homology of F. And the Gordon-Litherland pairing is a pairing on the first homology of your spanning surface given by this formula here. So you take the linking number of the transfer of A with B. So that's one component of the signature. The other component is the correction term, which is given by this normal Euler number of your surface. So that's also called the slope of the surface. So you take a parallel of the knot called K prime, and you take minus the linking number of K with K prime. And that's what this normal Euler number is. And they showed that if you take a spanning surface for the knot, then this pairing is a symmetric bilinear pairing on the first homology of the surface. And you recover the signature when you add to the signature of the Gordon-Litherland pairing, you add the correction term, the Euler number of F divided by 2. And then a simple observation here is that if you had started with an oriented surface, then the correction term vanishes, and the Gordon-Litherland pairing coincides with the symmetrized Seifert pairing. So that's the situation that was known circa 1978. And our goal today is to extend that pairing to knots and links in thickened surfaces. So throughout the rest of the talk, sigma will denote a compact, oriented, and connected surface. So we want to use, we want to describe a Gordon-Litherland pairing here, and then use it to define signature, determinant, and nullity invariants. And I'm hoping to outline two applications of this. One is toward generalizing Josh Green and Josh Howey's characterization of alternating links to alternating links in surfaces. And a second is to an application to virtual knot concordance. So the principal player in this, a sort of fundamental role is played by something called the relative linking. So let me talk about how we compute linking numbers in thickened surfaces. So if J and K are disjoint knots in a thickened surface, then we'll use just linking number of J with K to denote the intersection number of J with a relative two chain that bounds K relative to the top. So that's what it is formally. From a practical point of view, if you want to know how to compute this, you draw your knots in your thickened surface, and then you count the way you'd usually count linking numbers. You do it just as usual, except only counting where J goes over K. So here's a simple example to illustrate. For instance, if I look at J, the J curve and the K curve, so the J was blue until I redded it, and the K is green. But if you look at J and K, you notice J never goes over K. So up here is toward us, out of the page or out of your screen. Oops, not anymore. Let's see if I can get back there. So J never goes over K, so that linking number is 0. The linking number of J with K. On the other hand, the linking number of K with J, well, that K goes over J once, and the right-hand rule says that's a positive linking. So the linking number of K with J is 1. So immediately you see that the linking number defined this way is not symmetric. And the other 4 linking numbers are listed here. And they're all either 0 or 1 in this particular example. Of course, if you change the orientation of a component, you change the linking number. And so we'll define the Gordon-Litherland pairing now for knots with spanning surfaces F to be the average of the linking number of the transfer of A with B plus the linking number of the transfer of B with A. So this is there's an equivalent formula which appears in the paper, but this formula is maybe preferable because it's clear from the formula that this is a symmetric pairing. If I interchange A and B, I get the same exact quantity. What isn't exactly clear is that it's also an integer valued quantity. So dividing by 2 is a benign thing here. The things that I'm dividing by 2 are always multiples of 2. So this is integer value. So let me explain why that's true. And that is, it's easiest to see that if you argue locally. So when you draw the curves are actually generators for the first homology of our surface. So the surface here is shaded. It's a shaded portion. And the contributions only really come from when the curves interact with one another, where one crosses over the other, or they might intersect in the curve, in the surface. And if you think about when they cross, so for instance, this picture it's a little hard to see, but it's meant to denote a surface with a right-hand twist in it, and A is crossing over B in that picture. And if you take tau alpha, you push A above and below the surface, but you'll see that both copies of tau alpha go over B. So actually the linking number of tau A with B is +2 for this intersection, because you push it above and below the surface, but both copies actually go above the B because of the twist in the surface. So dividing by 2, of course, just removes the 2 from there, and we would get the linking number here, the contribution to the Gordon-Litherland pairing. I guess I should write it this way. The contribution to this is 1. And I guess I should have mentioned that the linking number of tau B with A is 0, because both copies of both push-offs of B go under A. So there's no contribution in this case. On the other hand, for the right-hand picture, if I look at tau A, the linking number of tau A with B, I get +1 here, because one copy goes above B and one copy goes below B when I take the push off in both directions. And if I do the same thing for tau B, I see that one copy of B goes above A and one copy goes below. And so the linking number of tau B with A is -1, and they cancel. So here, the contribution to the Gordon-Litherland pairing is 0. And since all contributions are one of these two types, possibly with B going over A, but they're always integral. Maybe that's a good place to stop and see if there's a question. Or maybe it's perfectly clear. So the generalized knot signature for a knot with a spanning surface F is defined completely analogously to the formula of Gordon and Litherland. Namely, you take the signature of this symmetric integral pairing, and you add to it a correction term given by 1/2 the Euler number, which is defined entirely analogously using this slightly different notion of linking. So that you can show is in some sense an invariant of the knot. One difference, though, is that this invariant may depend on the choice of the spanning surface. So a key question here is, in what sense is this an invariant of the knot? And again, Gordon and Litherland come to the rescue. They introduced this notion of S-star equivalence of spanning surfaces. And this is a mild extension of what's done for oriented spanning surfaces. So there you have the notion of S equivalence, and S-star equivalence just extends that to unoriented surfaces. So two surfaces are S-star equivalent if they're related by a sequence of ambient isotopies, addition or removal of a one handle or a small tube, and attachment or removal of a small half-twisted band. So this last picture, or this last move, is depicted in the figure below. So this is the move that takes you out of oriented spanning surfaces. If we just stuck with these two, that would give you the usual notion of S equivalence of Seifert surfaces. So it's well known that signatures are invariants of S equivalence of Seifert surfaces, and Gordon and Litherland showed that their invariants were their approach gave an invariant of S-star equivalence of spanning surfaces. And so a similar thing is true in this context. So if you you give me two spanning surfaces for a knot in a thickened surface, then the signature of the Gordon-Litherland pairing plus this correction term, that is unchanged under S star equivalence. So that's an invariant quantity up to S star equivalence. So I guess this corollary is an attempt to answer that question. And it says that these signature invariants depend only mildly on the spanning surface. And again, a simple remark, and this is just to reassure people who prefer working with ciphered surfaces. If you had used a ciphered surface, then this term vanishes, and the signature of the Gordon-Litherland pairing agrees with the signature as is traditionally defined. So in the context that we're in, you also get interesting invariants from taking the determinant of the Gordon-Litherland matrix and its nullity, so the rank of its null space. So for classical knots, this quantity on the right, the nullity is always 0, but it's not always 0 for knots and links in thickened surfaces. And those quantities are also can be seen to be unchanged under S star equivalence. So they depend only on the S star equivalence class of the underlying spanning surface. So that's all kind of the good news. The bad news is about existence and uniqueness of spanning surfaces. And really, this is meant to be interpreted up to S star equivalence. So some facts, so I'm listing as facts. I can't do, I really can't do justice to all the beautiful results in Gordon and Litherland's paper, so I have to assume some of them are facts. But they prove that all knots, any two spanning surfaces of a classical knot or a knot in S2, that they're S star equivalent. So really, there's only, for knots in S2, in a thickened copy of S2, there's only one S star equivalence class. And that's not true for knots in higher genus surfaces. So in fact, you don't get existence. So it's not true that all knots admit spanning surfaces. And you don't get uniqueness. It's not true that any two spanning surfaces are S star equivalent. It's almost true though. So it's not as bad as it sounds. So for the second point, it's easy to characterize when a knot admits a spanning surface, and it will do so if and only if the knot is what's called checkerboard colorable. So it's pretty clear that so let me define what it means to be checkerboard colorable. It's the usual notion. I can checkerboard color the complement of the knot diagram in the surface so that the colors alternate, say black and white, and no two regions of the same color are adjacent. So below here is meant to be a picture of a knot in the torus. So it's a simple two-crossing knot down here that I'm talking about. And that is not checkerboard colorable. So if you try and checkerboard color, you might shade this part. So I'm not going to use black and white. I'll use red and some other color, maybe just leave it white. But if that's red, then this is red, and that makes this part red too, because I go up from here across the boundary. And then you see that it's not checkerboard colorable. So now what is true though, is if you have a knot that's checkerboard colorable, then every spanning surface is either S star equivalent to the black surface or the white surface. So the bad news is not so bad. There are really just two sets of invariants. One for, you fix the coloring, then you'll have one set of invariants for the white surface and another set of invariants for the black surface. And right, my joke about this is I'm not colorblind, but I'm slightly lexistic. So I only think about the black surface. So I just never work with a white surface. It's always a black surface. If I have to work with the other surface, I change the color. So everything henceforth will be relative to the black surface. So, so let me give you the first application of these. And so a long time ago, Fox asked, what is an alternating link? And this problem was studied and is a celebrated result now, 4 years old, due to Josh Green and Josh Howie. And they gave a really beautiful geometric characterization of alternating links. And in particular, Josh Green showed that a link is alternating if and only if it bounds a positive definite and negative definite surface. And the goal in this application is to extend their methods and their characterization to more general three manifolds. And truth be told, truth in advertising, I only know how to do this for knots and links and thickened surfaces. So I'd be very interested to see more general results along these lines. But today we're just going to talk about three manifolds of the form sigma cross I. So some definitions that will help us. And I'm a little confused. I guess we started at 3:40. So I should probably
like
be
10 more minutes if necessary.
Okay, we should be finishing soon, I guess. So a link is alternating. A link diagram on a surface is alternating if the crossings alternate from over to under, and a link in a thickened surface is alternating if it admits an alternating diagram. So here's an example of an alternating link. And in fact, this is the same link as what appeared before when I was showing you how to compute the relative linking number. And a remark, actually, this is a theorem due to Nako-Kamada, which is if you have a cellularly embedded alternating diagram, then it's checkerboard colorable. In fact, a diagram is checkerboard colorable if and only if it's crossing change equivalent to an alternating link. So now if you give me a coloring of the link diagram, then I can distinguish the crossings into two types, type A and type B. And type A are the ones with incidence number 1, and they're drawn as here on the left, and type B are of this kind. And this is, well, there are a number of reasons why these are important. For one, whenever I have a curve going through this crossing, if I look at the Gordon-Litherland pairing of the black surface, and I look at the self pairing of this alpha, the surface, the black surface, goes through a right-handed twist as I go through this, and so the contribution will be exactly +1, and here it will be -1 for the same setup. And it actually is independent of how you orient alpha. Alpha could go the other way, and it's the same difference. So eta sort of counts the self-linking of curves going through that crossing. And it's relevant here because, well, let me, one more definition. We'll say a surface, a compact connected surface is positive or negative definite if the Gordon-Litherland pairing is. And so a lemma here, the first lemma, is that if you have an alternating cellularly embedded link diagram, then the checkerboard surfaces are definite and of opposite sign. So let me try and explain why that's true. And if you fix a coloring, the first observation is a combinatorial observation, which is that all the crossings will have the same type. They'll all be either type A or type B. And we'll assume we can fix the coloring so they're all type B so that the incidence number is always -1. And if we do that, then a simple closed curve on the black surface, its Gordon-Litherland pairing will just be the sum of the incidence numbers of all the crossings that it goes through. And since all of those are -1, the self-pairing of alpha will be negative. for every curve on the black surface. And a corresponding result will be true for the white surface. In fact, if you switch the coloring, the types of the crossings change, so the incidence numbers change. And so if the black surface is negative definite, the white surface will be positive definite. So that proves one direction of the next proposition, which is a characterization of alternating diagrams. And it says that a connected checkerboard colorable link diagram, which is cellularly embedded, it will be alternating if and only if the two checkerboard surfaces are definite and of opposite sign. So this really, proving this proposition amounts to proving the converse to what we just saw. And that amounts to a little more work, both noticing that the difference between the signatures in absolute value for the Gordon-Litherland pairings for the black and the white surface will be, they will sum to the sum of the first Betti numbers. And playing around with the correction terms, you can see that all the crossings will have to necessarily have the same type. They'll all be either type A or type B, depending on how you chose the coloring. And then it's easy to see that that's equivalent to the diagram being necessarily alternating. So the theorem that generalizes the characterization of Green and Howey is to show that this actually holds for any alternating link, not just the diagram. So if you give me a non-split link, that link will be alternating if and only if it admits a positive and negative definite surface. And I don't think I have time to go through the proof. And in fact, I wanted to get to the second application, which is to concordance. That's sort of the new thing. So let me skip ahead to that. So what does it mean to be virtually concordant? Well, two knots are virtually concordant if you can find a cobordism, so they're both in thickened surfaces. If you can find a three-manifold co-bounding sigma 0 and sigma 1, as well as an annulus drawn here in the thickened three-manifold co-bounding K0 and K1. So that's what the notion of virtually concordant is, and it's virtually sliced if it bounds a disk in some thickened three-manifold. These definitions are due to Turaya. And our theorem here is that if your knot is virtually sliced with spanning surface F, then the signature is bounded above in absolute value by the nullity, and the determinant is a perfect square. So these are the familiar conditions from classical knot theory, right? A classical knot is sliced. That implies the determinant is a perfect square. And usually you just say that the signature has to be 0, but that's because the nullity is always here. Here, we only get a bound as good as the nullity, but we do recover the classical result when the nullity is here. And this result took us a while to sort out. And a key step was proving the existence of what you might call spanning manifolds or unoriented Seifert manifolds for knotted surfaces in four manifolds. We're really working with four manifolds that come as thickened three manifolds. But we wanted to know under what conditions, given a knotted surface in W cross I, under what conditions can you find a three manifold embedded in W cross I with boundary, that knotted surface. So this is just like finding a Seifert surface for a knot, one dimension up. The complication here is that E is not necessarily oriented. So V is not necessarily oriented. And let me just finish by stating this theorem. And it's a necessary and sufficient conditions to have such a three manifold. And it turns out that the conditions are that the Euler number of this knotted surface is necessarily vanishes, and the knotted surface is homologically trivial with Z2 coefficients. So, and then this theorem is proved using a techniques from obstruction theory. So I'll end there. Thank you.
Okay. Thank you very much for your talk. So are there any questions in the audience?
Yeah, so I have a question. So I just wanted to ask you, like, so as a corollary to Joshua Green's paper, so we had that for special alternating links, knots or links. So every Seifert surface can be given by Seifert's algorithm on some diagram, right? So is there some like that kind of corollary for this result in sigma cross I?
I don't know off the top of my head. I thought we'd thought about this. There is, I mean, maybe, yeah. I don't want to punt it to Josh, but I think that the issue for us is that we don't have an analog of Morisugi's theorem that that Seifert's algorithm always generates the minimal genus Seifert surface. I think that's true in our context. It would only apply to knots that admit oriented spanning surfaces. And I guess I should have pointed out that the set of knots to which these results apply, the ones that admit spanning surfaces, are actually quite a bit broader than the ones that admit oriented Seifert surfaces. So in the classical theory, right, the Gordon-Litherland approach is a really practical way for computing signatures that you know exist because you get them from Seifert surfaces. But here we actually, most of these knots don't have Seifert surfaces per se. But that's an interesting point of view, and I'll have to think about it more. Thank you for the question.
Any other question?
I had a question. So you mentioned that if you're in a, say I got it right, you got a checkerboard colorable knot in a thickened surface, there are at most 2 S-star equivalence classes of spanning surfaces for it. Is that the remark?
Yes, that's right.
And I mean, there's just one if it's, you know, S2, your surface. So yeah, I mean, can you say more, like what distinguishes the S-star equivalence classes, and like for which knots? Is there only one?
So that's a really good question too. There's a sort of funny, there's a funny class of knots for which you know you have 2 S-star equivalence classes, but yet the signature invariants end up being the same. And I don't know how to characterize that family in thickened surfaces. And I guess, you know, the characterization of the spanning surface is really the relative homology class of the spanning surface. So in sigma cross I relative to K, if you look at that homology group with Z2 coefficients, it's the Klein 4 group is what it is. And then there are 2 elements that the spanning surface can be in that group. And so these spanning surfaces are one or the other. And in some sense, in S2 cross I, there really are 2 as well. But there's a way to kind of flip S2 over itself and get from one to the other, which you can't do when the surface has genus. So that's an interesting point.
Okay, I get it. Yeah, thanks.
Okay. Well, thanks again for your talk. Mm-hmm.